In this video, we want to look at derivatives of integral functions. Okay, so we're going to start with something easy, one that we could do without any, by just sort of stepping through the process. In fact, let's go ahead and do that. Okay, so if I wanted to find g prime of x, the rate at which g is changing, okay, I would take the derivative with respect to x of the integral that we have here. Well, we can just work our way through that. When I use the fundamental theorem of calculus, this would be t cubed over 3 evaluated on the interval from 1 to x. Right? So the upper limit is changing as x changes. All right, and then we would say, okay, let's leave the derivative with respect to x out here, and we would get x cubed over 3 minus 1/3. Now, if we take the derivative of each of those things, the derivative with respect to x of x cubed over 3 returns x squared. Okay, the derivative of a number like 1/3 is 0. So we just get x squared back again. Okay, now if you look at this, x squared is simply the integrand function evaluated at the upper limit of x, right? Now that should kind of make sense because we know that g is the antiderivative of f of t equals t squared. So we know that g is an antiderivative of f, therefore g prime is f. If it's g prime of x, it's equal to f of x, all right? So the derivative should be the integrand function simply evaluated at x. Now graphically, we can see how this would work. Let me make a little graph over here. Here's our function, and I'm going to exaggerate. The scaling won't be 1 to 1, but we're going to integrate from 1. Let me just put that here where you can see it. Okay, that would, we'll say this is where x equals 1. So the lower limit is fixed, right? But the upper limit, switch colors here. The upper limit, let's drop that right here, okay, is a variable x, so it's moving, okay? We'll assume it's increasing. So that side is changing, okay? Well, g is the area function, right? So g equals the area. How fast is the area changing? Well, it depends on how fast x is growing. Okay, I'm going to draw a rectangle over here, okay? And let's just say that this grew, x grew by delta x, or delta x right here. Well, the height of this is just the function f. So the change in area, just under here, change in area is equal to f delta x. Now, if I want to get the rate at which the area is changing, I'll take that over delta t. I'm sorry, I'll do that over delta x. Okay, that's how fast it's changing. Okay, and if I throw in the limit as delta x goes to 0 of both sides, then I can say, I'm not going to write it in, but I can say dA dx, which would be dg dx, is simply equal to the height of the function f at that particular, wherever the boundary is, wherever x happens to be. Okay, so we can see if we were to put little rectangles in, the growth rate is small when f is small, and the growth rate is going to get bigger as f gets bigger. So the rate at which the area is growing is simply the value of the function, right? Now this is useful if we were working with a function where we couldn't find the antiderivative. There are functions where that is true. So let's go on to another example here. Let's say that g of x is equal to the integral of the sine of, we'll put it t squared. I should put that in the parentheses. Let me. And let's integrate from 0 out to x of the sine of t squared with respect to t. Okay. We don't know what the antiderivative of that is, okay? But we can apply the same principle, okay? This function right here is the integrand is little f of t right now. So the sign of the input squared is little f of t. We know that g is the antiderivative of that. So g prime of x needs to equal little f of x, okay? So the function, that would mean we would just take the signed function of the variable squared. In this case now, since the variable is x that we're putting in, it simply gives us the sine of x squared back again, okay? This would be the height of the function at the right limit of x, or upper limit of x, okay? So the function height is sine of t squared. When we're at x, that's just the sine of x squared, okay? Now, a couple of things that could make this a little bit more complicated. So we don't actually, you can see we sort of undo taking the antiderivative, right? If we wanted to, we could think of this in a slightly different way. We could say g of x is equal to whatever the antiderivative of the integrand is evaluated at x minus the antiderivative evaluated at 0. And then we could take the g prime of x is the derivative of those things. So it would be f prime of x minus 0, because the derivative of a constant is 0. And so this just gets us back to f of x, as we said before. Okay, a couple little tricks. What if we flip the limits? So this went from, let's say, x out to pi this time, okay, of the sine of t squared with respect to t. Okay, so let me write over here, little f of t would be the sine of t squared, okay? And little f of t is equal to f prime of t. I could also say little f at x is equal to f prime at x, okay? And little f of x would be the sine of x squared. Okay, so you need to understand all of that, okay? So what happens here? Well, we have the limits upside down. So we would like x to be on the top. So a really good way of handling this is take the limit, the negative of g of x is the integral from pi to x of the sine of t squared dt. And then this just becomes like the last problem, okay? We could say, oh, negative g of x is equal to, we don't know what big F of x is, minus big F of pi. But we do know that when we take the derivative, negative g prime of x is going to have to equal, we can put this back in, and we're going to get f prime of x minus 0. Okay, well, what is f prime of x? That is the sine of x squared. Looks a lot like the integrand. Whoop, minus 0, we don't even need to write that in. Okay, now that was negative g prime of x. So what is g prime of x? It's simply negative the sine of x squared. Okay, so that's what you can do. You also could have just simply not put the negative in, not flip the limits, and said, oh, this would have been that g of x in this step right here. G of x is equal to f of big F of pi, the antiderivative, minus big F of x. So g prime of x is 0 minus f prime of x, which is negative sine of x squared. Okay, so when the variable is the lower limit, okay, then you're just going to get a negative thrown in, because we have that rule about flipping the limits. That would work nicely. Okay. Now, where it gets a little more complicated is when the upper or one of the limits, or both of the limits end up being functions. Okay, so let's consider in general that g of x is equal to, let's do the integral from 0 to 2x, some function f of x, whoops, f of t, I'm sorry, let me change that, f of t dt. Okay, so what's going to happen here? Let's go back to the graph. Okay, so if I were to graph this function, it's just a generic function going up like this, and we're going to start integrating it at 0, but we're going to go out to some value of x out here. All right. So we're going to have some t value. Okay. Okay, which is equal to 2x. All right. Now here's the problem. When x changes by 1, t is going to have a double change here. Okay, so whatever delta x is, we're going to have 2 delta x's of width change, because t is equal to 2x. So we get a delta x and another delta x, and it's still f tall. Okay, so what's happening to the area? Okay, the change in area, which would be the change in g, would end up equaling f times 2 delta x. All right. So if we want to find delta A over delta X, that would end up being twice F. Okay. So therefore, if we make this into a derivative by letting delta X go to 0, or the limit that delta X goes to 0, we would get that G prime of X is twice F at X. Okay. So notice the right limit is at t, x would have been back here somewhere. Okay, so that's where x is, and the right-hand limit gives us a value way out here at 2x. All right, so we're evaluating. Oops, and I have to be careful here. Where are we finding the height? We're not finding the height at x. We are finding the height out at 2x. So if you give me an x value, the upper limit is all the way out here at 2x, right? And because we have a 2x there, every time x changes by a delta x, okay, out there at 2x, the rectangle is going to get doubly wide, 2 delta x wide, right? So we need to evaluate the height at 2x and multiply by the double width factor. So the 2 that we see right out here is a chain rule 2, which is the derivative of that. Okay, so what is the solution to this? Okay, it's that generically, if this had been g of x is equal to the integral from 0 to 2x of the sine of t squared, okay, and we go to take the derivative, we would chain roll the 2x, and we would get a 2. And then we would take the sine of t squared and substitute 2x. So we would get a 2x squared. Okay, because the sine of the quantity 2x squared is the height where we are. And then we multiply by 2 because the widths are changing twice as fast. All right, and then the lower limit won't matter. Okay, so that's what we have to do here. If we want to work it through the notation, g of x is equal to, I'm going to skip down, it will be big F at 2x minus big F at 0. And when we go to take the derivative of that, we have to chain roll the 2x, take the derivative of 2x, which is 2f prime of 2x minus 0. And f prime was the original integrand function. So that's 2f if little f is the integrand function evaluated at 2x, and the integrand function was for as a function of t was the sine of t squared. So when we substitute in 2x, we get the answer that I already said we would get, the sine of 2x squared. Okay, now it's not that common to have a function for a limit. It's much more common to simply have x for a limit. Now let's go ahead and do one final example. Let's say we had g of x is the integral from 2x up to x squared of, we'll put in the sine of t squared dt, right? We don't know what the antiderivative of this is, but g of x, we could say, is the antiderivative evaluated at x squared minus the antiderivative evaluated at 2x. So now the upper limit and the lower limit are changing at variable rates. Okay, so if I want to find g prime of x, I have to take 2x times f prime of x squared by the chain rule. Okay, minus 2 times f prime at 2x. Okay, and remember, what is f prime of t is the sine of t squared. It's the same as f of t. And so we can say, this answer will be 2x times the sine of, we have to put in x squared squared minus 2 times the sine of 2x squared. Right? We should probably clean that up and say this is 2x times the sine of x to the fourth minus 2 times the sine of, and I'll put it in parentheses, 4x squared. That'd be a better way of saying it. That would be the derivative of the integral function. It's a little bit roundabout to take derivatives of integral functions. Doesn't happen too often, but when it does, that's how you do it.